Okay, so we're going to look at the rate laws now from a different point of view. We're going to look at how concentration changes over time, but we're going to look at it in a more flow kind of way, I guess. So our rate law simply tells us how the rate of the reaction changes as concentrations change. But what we're going to do now is look at how the reactant concentration changes over a period of time. And to do this, you have to know what the order is. And so we're going to zero in on specific orders and simplify it. We're not going to do anything really complicated here. This kind of process uses calculus by integrating a rate law. And if you've taken calculus, you have an idea what that means. Don't worry, we're going to do the integration and you're not required to understand that, but basically what you're doing is integrating over time. You're trying to find out what the equation will be over time relating to concentration. And we're only going to do a few, and it's been, it'll be integrated for you. It's not anything you have to know how to do. And then what we're going to do is use these integrated rate laws to actually graph our data, and we can determine rate laws that way. All right, so if we know that a reaction is first order, so remember what's first order? Rate equals K times some concentration raised to the first power. So that's my first order rate law. If we integrate it, and here's another way of writing it. So we know that rate equals the change in concentration over change in time, and it equals to Ka to the first power. It's negative because the reactant is decreasing over time. So if we integrate this over time, we end up with this. Now, I've written it 3 different ways, and the reason I did that is because some people are not as comfortable with natural logs as other people. So it turns out that they're all 3, again, are the same thing. The natural log of the ratio, and what are these? What do all these mean? A sub t means what's the concentration at time t. So concentration. This is concentration at time 0, or initial concentration. K is our same constant that we've had, so that's just our constant. And then T is just time, whatever time we're talking about at time T. And so what this does is it tells you, okay, let's say I started with 0.5 molar. After 50 seconds, what is my concentration? And so that's the kind of information that you're getting. So in here, you're going to have to know all but one of them, and you can solve for one of them. Now, notice this equation over here is actually the inverse of this equation. So if you take the natural log of something and you want to undo the natural log, it's taking e raised to that power. So if I undo the natural log on the left, I get AT over A naught. If I undo the natural log on the right, because you have to do it to both sides, that's raising negative KT, raising e to the negative KT. So these equations are the same, they're just written in different forms. This equation on the left is probably easier if you're trying to solve for time. This equation on the right is probably easier if you know time and you're trying to solve for one of the concentrations, because it's just, but if you're comfortable, if you're good at math and you're comfortable with undoing these equations, then you don't have to remember all the different versions. And believe it or not, this equation right here is actually also the same, just written in a different format, because if you take the natural log of a ratio, it's actually the natural log of the numerator minus the natural log of the denominator. This is the natural log of the whole thing. So any 3 of these can be used to solve an equation. Use the one that seems the easiest for you to solve. So again, AT is the concentration of the reactant at a particular time, T. T is the time, and A naught, again, A0 is the initial concentration. And K is just our constant. Sometimes you just want to know what is the fraction, how much is remaining at a certain time. And so if you don't necessarily know what the initial concentration is, but you just want to know what's the fraction remaining, you can just find that ratio. Or a lot of times you'll solve for one or the other. So let's look at an example. The decomposition of N2O5 is first order, and it has a rate constant, so this equals K. And so here's a typical kind of question. If the initial concentration of N2O5 is 1.65 times 10 to the minus 2 molar, or let's write that, so that, what is that, 0.0165 molar. So if that's my initial concentration, what is the concentration after 825 seconds? So that's time. And what I'm looking for, what is the concentration? So I'm looking for A at time T, which is 825 seconds. So if you heard what I said on the previous slide, the easiest equation probably to use, if you already know T, is to use the equation that has E in it. So let's look at that equation. Yep, so it's this equation. So the concentration at time T divided by the concentration at time 0 equals E to the negative KT. And do be careful, don't lose that negative sign. So we have K is 4.8 times 10 to the minus 4th inverse seconds per second. And notice it's first order, so it doesn't have molarity in the units. T is 825 seconds, so they're in the same, you want to make sure they're in the same unit so that the seconds will cancel. So if I plug in everything, actually I rearranged it beforehand, so I multiplied both sides by initial concentration so that I could solve for final concentration. And if I plug those numbers in, so here's the initial concentration, 1.65 times 10 to the minus 2 molar, E raised to the negative 4.8 times 10 to the minus 4th, times 825, so you want to do that before you take the E of it. On your calculator, your E button should be right under your natural log button, and so usually it's a second natural log button depending on your calculator. So E raised to the negative 0.396, because that was the 1.65 times 10 minus 2 times 825 is 0.396 negative. If we take E raised to that, you get 0.673. And then if you multiply 0.673 times 1.65 times 10 minus 2, you get 0.0111 molar. Just take a minute and think about it. Remember, this was 0.0165. Hopefully this number should be less because time has gone on and some of this reactant has decreased, and that does make sense. So that would be my final concentration if my initial is 0.0165 molar. So that's how you do this kind of problem. If you have a second order integrated rate law, so if you know that your reaction is second order, we can also integrate. So this is what that means. It means rate equals, and just rate is just negative delta A over delta T. Rate equals K A raised to the second power, because that's second order. So if we integrate, and again, this is calculus, so you just like a little magic, how we got there, just the results of it. And this is the equation for second order. So notice that it's a little bit different. 1 over the final concentration equals KT plus 1 over the initial concentration. And again, there's different ways that you can write this. It's a little easier to solve than natural logs, because how do you invert? To solve for something in a denominator, you just invert it. So it's a little bit easier to work. You can also, you know, if you rearrange it, 1 over AT minus 1 over A naught equals KT. That's just another way to write it. It doesn't really matter. But just be careful with this one too, because you want to make sure and take your fractions. Or if you're solving for something that's in the denominator, make sure to invert it. I think I've got an example here. All right, so this is a second order decomposition. And now I can't know by just looking at it that's a second order, and so this problem is telling us that it's second order. So for these kind of problems, they're going to tell you if it's first order or second order or zero order. They might not tell you directly like this one, like they might not say this is a second order reaction. They might say the rate law for this equation is HI squared. That tells you it's second order right there. So they might not tell you directly, but in some way they're going to give you that information if it's first order or second order. And it's always, the integrated rate laws are always the ones that you're using when it's concentration changing over time. Okay, anyway, so they're telling us it's second order, and they're telling us what K is. And they're wanting to know, this time they're looking for time. So how much time, what is T, does it take for the concentration of HI to drop from 0.010 molar to 0.0050 molar? So in this case, we're looking for time. So we can, let's just write that equation, 1 over AT minus 1 over A naught equals KT. So we're solving for T. Now you don't, some people are not as good at rearranging algebraic equations. So just plug in the numbers if that's easier for you. Let me do it over here. So this is 1 over, it's the second one, 0.0050 minus 1 over the initial 0.010 equals K 30 T. One divided by 0.0050 is 200. And 1 divided by 0.010 is 100. So 200 minus 100 is 100. Divided by 30 is going to equal T. So what is that? 3.33 minutes. 3.33 minutes. Let's see what I did here on the PowerPoint. Yep, so there's our equation. Here we go. We plug 30 in here. I'm going to erase this now that I've written that so you can see what's happening here. Notice my units. I was able to just sort of figure that out because of the minutes, because that's what my rate is in. But notice what happens with the units. So this is in molarity. Well, it's actually an inverse molarity, right? 1 over molar, 1 over molar. So when I do this number, it's 200 inverse molar minus 100 inverse molar. So that becomes 100 inverse molar. Over here, it's inverse molar, inverse minutes. So if I divide this side by 30 inverse molar, inverse minutes, the inverse molar cancel, and we have the inverse of the inverse minutes, which turns out to be minutes. So my units should cancel out. Now I've probably written over what's going to come next. So yeah, 200 minus 100 divided by 30. Go ahead and erase this now that I worked it through. T is 3.33 minutes. And again, my units cancel. And this is 1 over minutes. So it ends up going back on the numerator. That's the type of problem. So this is second order. Second order seems to be just a little bit easier to solve because you've got fractions. And I wouldn't, don't work, just do it step by step. Do what's easy for you to calculate. That's why we have calculators. Now, we can have a zero order integrated rate law, and this happens to be the zero order rate law. The concentration of A at time t is what that should say, equals negative KT plus the initial concentration. And you can use that the same way. All right, there's something called a half-life. The half-life of a reaction is just the time required for the reactant to decrease to 1/2 of its initial value. For a first-order reaction, half-life doesn't matter what the initial concentration is. And so actually, if you plug in, so if you have, let's see, right, we had AT over A naught equals e to the minus KT. Remember that equation? That was first order. If AT is half of what A naught is, then this just ends up being 1/2 equals e to the negative KT. And if you undo the e, that means it's natural log of 1/2 equals negative KT. And the natural log of 1/2 is 0.693. And so the half-life will equal negative 0.693 over K. So that's what's coming up here. Let's erase my, hopefully you don't mind this, that if you see me doing it, probably makes more sense than just seeing the equation up here. Again, this was the original. If you look back on that, this is another, I didn't use the e, I just used the natural log equation. So again, if t is half of what the original was, this ends up being 1/2. And so the natural log of 1/2 is equal to negative KT1. And so that's a helpful equation. T1/2 equals 0.693 divided by K. So just kind of a little hint there that they might not give you K in a problem, but they might tell you what the half-life is. And so you can find K, because of course K will equal 0.693 over the half-life. So you can find K if you know the half-life, you can find half-life if you know K. And again, this is first order only. So if it's a first order equation, it doesn't depend on the concentration at all. This is what a first order reaction looks like. As you plot after the first half-life, it's half the original amount. After the second half-life, it's half of what we had on the previous, and then it's half again. So after each half-life, it goes down by half, and you end up, this is sometimes called an extinction curve, it kind of coming down, and you can imagine eventually it's going to level off. And in all practice, obviously it never quite reaches zero, but in all practicality, when you're measuring concentrations, eventually you get to a point where you can't measure concentration anymore, and technically the concentration goes down to zero. So it just keeps going. After each half-life, it's a half again. Let's just look at an example here. So the rate constant K for this equation, this is a first order, they're telling you it's a first order reaction. Here's what K is, and they want to know what is the half-life. So that's pretty straightforward. Half-life equals 0.693 over K. Plugging in that value, 0.693 over 2.2 times 10 to the minus 5th. Inverse second, so notice my inverse seconds become seconds. And so it's, what is that, 31, 1, 2, 3, 4. 1, 2, 3, 4. So 31,500 seconds is the half-life to this reaction. Sometimes you can use your half-life, especially if you know if it's first order. If you go back and look at one of the reactions where the the concentration fell from like 0.0165 down to 0.0111, you can kind of get an idea. If you know what K is, you can find out what half-life is, and then you can get an idea that, well, if the half-life, you should get the concentration to be about half, and then you can kind of estimate if your answer is correct or not. Now, a second order reaction, the half-life does depend on the initial concentration. And so the half-life will get larger as time goes on, because as your concentration decreases, your half-life is readjusted. So the half-life is not constant for a second order reaction. It will keep changing, and it'll get longer and longer because your concentration is decreasing each time. So it turns out that for a second order equation, T1/2 equals 1 over K times the initial concentration. So again, once you get half to the half-life, the initial concentration is half, and so the T1/2 has to be recalculated after each half-life. And actually, it's continuous, so it's not really, but you get the idea. So each succeeding half-life is twice that of its predecessor. And then if you have a zero order reaction, this is how you can find the half-life. It's the initial concentration divided by 2K. We can also use graphical methods to deduce if your reaction is first order or second order. We're only really just going to focus on first order, second order, and maybe zero order. So what we're going to do is rewrite the first order concentration time, the integrated rate laws, and we're going to write them in a y equals mx plus b format, which you know is the equation of a straight line. So if we look at, so this is, remember, this is first order. This is the first order rate law, the natural log, and I've gone back and I've rearranged it because remember we had every different type of way of writing it. Remember, it was originally natural log of AT minus the natural log of A naught equals negative KT. So all I've done is I've moved the natural log of A naught onto the right hand side to get it in the form of y equals mx plus b. You know that this is the equation of a line, and so what does this tell us? If we plot time on the x-axis versus the natural log of the concentration on the y-axis, we should get a straight, if it's first order, we should get a straight line where the slope is equal to the k value, the negative k value, and the y-intercept should be the natural log of the initial concentration. So I think we'll do something like this in lab, but let's take a look at an example. So again, if you plot natural log of A on the y-axis versus time on the x-axis, you should get a straight line if it's a first order reaction. That will hold true. So here you can see, here, this was some of my data. So at time 0, 600 seconds, 1200 seconds, so forth. These were my initial these were my concentrations at those different times. Initial concentration. Oh, this is that same equation, the 0.0165. And I can't remember, you might go back and look at that problem. I can't remember what the time was, but obviously the 0.0111 fits in right here. So that was, oh yeah, it was 825 seconds, wasn't it? So that 800 is kind of right between those two. So that makes sense that, that our data holds. Anyway, back to this problem. So here's our concentrations. What I did is we took the natural log of this number. So the natural log of 0.0165 is negative 4.104. The natural log of 0.0124 is negative 4.39, etc. So if we plot natural log of concentration versus time, and we get a straight line, that tells us that this reaction is indeed first order. We can also find the slope of this line. And so if you graphed it on the computer or whatever, you can find the slope of this line, and the slope will equal negative k. And in this case, because the slope is negative, k will be a positive number, which it should be. So Now, if it's a second order rate law, then, and we rearrange this equation, what we should get is, again, if we plot time on the x-axis, and this time 1 over the concentration on the y-axis, we should get a straight line where the slope equals k and the y-intercept is 1 over the initial concentration. And so, again, yeah, plot 1 over a on the y-axis versus time. And so the next equation will show it. Okay, so here's our data, time. Here are concentrations. Now, notice this one. This was trying to determine, is it first order or is it second order? So the first equation, which is this red line over here, they found the natural log of the concentration. So the negative log of 1 times 10 to the minus 2 is negative 4.605. The negative log of 6.683 times 10 to the minus 2 is negative 4.98. And that, if you plot that, that's the red, oh, no, sorry, this is the blue line. So this is time versus natural log. And notice that the blue line, which is this data, this on the y-axis and this on the x-axis, turns out not to be a straight line. They drew the red line in there to show you that that's what a straight line would be. So this is not a straight line. So what that tells you is this is not, it doesn't fit, it's not a straight line, so it's not going to be first order. Because natural log versus time does not give us a straight line. However, now 1 times 10 to the minus 2, 1 over that is 100. 1 over 0.683 times 10 to the minus 2 is 146, and so forth. So now we've taken the 1 over the concentration and plotted that versus time, and that does give us a straight line. So again, this tells us it's second order. And this is what I believe we're going to do that in one of the labs where we'll plot. We'll be given the data and we'll plot natural log versus time, and then 1 over concentration versus time, and see which one gives us a straight line. And of course, if it's not first order or second order, you won't get a straight line. And there are many more complicated, but again, we're just sticking with this, with the straightforward. So here's just one more example. Butadiene reacts according to this equation. The following data were collected at a given temperature. Not telling you the temperature, but it doesn't matter. Is this reaction first or second order? So that's the first thing we want to find out. What is the value of the rate constant? And then what is the half-life? So we can do that like I just said, by plotting. So you could actually plot time versus concentration, and if it's a straight line, it's 0 order. But in this case, we're looking whether it's first order or second order. So what we want to do is plot time on the x-axis and then the natural log of this. So I'm going to make a chart where I do the natural log of 0.01000 is negative 4.605, so forth. So we're going to do the negative log versus time. So here you can see what I did. I did 1 over concentration versus time, and here's natural log versus time. So I'm going to plot them individually. So I'm going to plot that. Let's see what's on the next slide. So you can see here, this is natural log versus time, and that does not give us a straight line. It gives us a curvy line. So it's not first order. And then 1 over the concentration versus time does give us a straight line, so it is second order. We also, once we draw this line, we can find the equation of the line. So once we find the slope, we'll be able to find what K is. I didn't put the equation of the, if you graph it yourself, you can find the equation of the line, like from Excel or something like that. So it turns out this is the equation of this line. And so K is equal to 0.0613 inverse molar inverse seconds. And it's second order, so that's the correct units. And then finally, you can find T1/2 by using our second order rate law half-life, 1 over K over A naught. So our initial concentration was 0.010, our K 0.0613, and so this is our half-life, at least for the first interval, and it'll change over time, but they're asking for it from the first interval. So I hope that makes sense to you. And like I said, we'll be practicing this. I think there's also a worksheet on Canvas, and we'll be practicing this in class, in lab. So this is just a summary. If it's zero order, rate equals K. There's no concentration that affects it. Here's the integrated rate law. Here's the half-life. A straight line of concentration versus time. Concentrations versus time will give us a straight line if it's zero order. If it's first order, here's the rate law. Here's the integrated rate law. And 0.6, here's the half-life. And then a straight line will be given if it's natural log versus T. And then if it's second order, here's the rate law. And here's the integrated rate law. The half-life is 1 over K A naught. And then a straight line will be given 1 over A versus T. So that's a nice little summary.